Hi there. In this video, we're going to talk about exact differentials, line integrals, and thermodynamic potentials. And we're going to look at what is the relationship between all of these things and how they work in thermodynamics. So we can start by looking at a roller coaster. And in a roller coaster, we are at a certain height that's at position A. And we have this roller coaster that's sloping down via this curve all the way to position B. So this analogy is usually used to define what line integrals are. If we just isolate one specific point on the roller coaster, such as that, an arbitrary point, we would understand that there's different forces acting on the roller coaster, primarily being the force of gravity that is pulling it downward. And of course, it would have components in the various directions. So we have force that's actually a vector valued function. So we have F with an arrow on top of it to represent that it's a vector. And then this force is acting along a differential element of this particular curve. So we can show that as perhaps that. So this is a differential element, dr. And if we wanted to find the work done along this little differential element dr, which is also a vector valued function, then we know that work done is actually equal to force times distance. If we have any kind of object, let's just say we have a table, then we have something on top of it, and we want to know the work done to move this object a certain distance, maybe delta x, and we have an applied force that's has acted on this object, then the work done is equal to this force multiplied by this distance. So in the same way, along this little differential element dr, we have F, and we also have dr, and we take the dot product between the two. So this dot product actually means that now we have a scalar that results. So this is the work done across this little differential element. So if we wanted to find the work done across the entire length of this curve, then we would have to add up the work done across a differential element split along this entire curve. So in other words, what we need to do is we have to sum up the little work done across this entire curve. We'll call that curve C. So this is actually what is a line integral. If we now think about perhaps the roller coaster, it has come here from point A to point B, and let's just say it loops back. It goes back to A. We do often see these kind of designs where they go out in an arc and go up and all of this kind of thing. So if it does do that, it means that there will be a differential work done that would have to be added up across this entire length of this curve from A to B and then back to A. So the point that I'm making here and what all of this is about is that there is a clear work done across the entire length of this curve. There will definitely be a number. There are times where if we do compute something like this, we find that when we integrate or sum some kind of function from A to B to A, we find that we get 0 as a result. And perhaps the easiest illustration of that would be potential energy. If we have a function that is described by this potential energy, and if we integrate that function along this closed curve from A to B and then back to A, then we find that we get 0. So when that is the case, this type of function is called an exact differential. So the way we look at exact differentials is that if we take the line integral of an exact differential along a closed path, such as from A to B and then back to A, then we see that we get 0. Because if we think about it in terms of potential energy, yes, we can see that there is a potential energy change from A to B because there is a change in height. So that change in height is what actually affects the potential energy the most. However, if the roller coaster returns back to where it started, there is actually no change in potential energy, and therefore this is why this entire thing would be 0. So we can now extend that to different types of quantities in thermodynamics, or this kind of thinking, or this kind of logic. But perhaps before that is that we can look at this integral, this f dot dr, and there is a way to split it up. So if we have something like f dr, it can be split into two parts. such as q dy and p dx. So let's just say that points like that. And perhaps we can think of this quantity FDR as being traveling in two different paths, q dy plus p dx. So we can write this integral of FDR as this integral of p dx plus q dy. And you would recall that we said that if this is an exact differential, then this will be 0. So let's just take this p dx and q dy and let's just represent it in terms of a function differential. So an exact differential also has the form, let's just say that we have z as a function of x and y. We can write an exact differential of this function dz is equal to dz dx times dx plus dz dy times dy. So if z is an exact differential, in other words, it follows all of these properties that we just described now, if we find the line integral of dz and we find it 0 and it can be described in this particular form, then it is an exact differential. So if we compare this to p dx and q dy, we can see that this dz dx is just p and this dz dy is just q. If we look at this curve and we see that if we integrate FDR, we definitely will get a value every single time. So work is not an exact differential or a state function. So when we're talking about exact differentials, another word for this is state function. So work and heat are not state functions. There will definitely be some kind of value if we integrate it along a closed path. On the other hand, if we have quantities like internal energy, enthalpy, the Helmholtz free energy, and the Gibbs free energy, and even entropy. So these things here actually are exact differentials. They are state functions. So another characteristic of state functions is the fact that if we look at A to B, if it doesn't matter how we go from A to B to A and we still get 0, it also means that it doesn't really matter how we get from A to B to A. So let me just say that once more. If we go from A to B to A and we're going to get 0 if we integrate this exact differential, it doesn't really matter how we go from A to B to A. So let's just say, this green curve that I've drawn is one of the ways. And let's just say another way is something like from A to B in that way. That's there, then there, and we come like that. And let's just call this original green curve C and this new curve something like, we'll call this C1 and C2. So it doesn't matter if we went along C1 or C2, we will still get 0 if we integrated it as a exact differential. So it doesn't matter how we actually go between two different points in this thing. So another characteristic of exact differentials is that we say that they are path independent. So exact differentials are path independent. It doesn't really matter how we get between different points on a graph of this kind. We have written z in this way. We've seen that it's a function of f of x and y, and we've written this exact differential in this form. Let's now extend it to thermodynamic potentials. We saw in the last video that we had the Gibbs energy, and we saw how it was equal to U plus PV minus TS. So we can see that the Gibbs energy is actually a function of pressure, temperature, and volume. So this is for a closed system. So you'd remember from your studies of elementary thermodynamics that a closed system is some kind of system in which energy can come in and out of the system, but not mass. So there's no transfer of mass or particles or anything like that into the system or out of the system, but energy can come in and out of the system. So if we take the differential of this in the same way that we have done for dz. So we get dg is equal to du plus pdv plus vdp minus tds minus sdt. So we've used the product rule here. You'll remember with the product rule, if we have a differential of, say, uv, then this is equal to v du plus u dv. So anyway, so this internal energy du, we can rewrite that using the first law, and du is actually equal to dq plus dw. So this is the first law of thermodynamics. However, we can use our definition of entropy, and this dq becomes Tds, and W becomes minus Pdv. And we just write what's left. So we have plus Pdv. So this term du is actually Tds minus Pdv. So then we have Pdv again. Then we have plus Vdp minus Tds minus sdt. So those two terms become 0, and Tds and minus Tds also become 0. So what we're left with is dg is equal to vdp minus sdt. Let me just write on the side here what I've done with this du. We've said that du is equal to dq plus dw. This is the first law of thermodynamics. And then we've also used the relation that dq is equal to Tds. This is also a definition, and I will explain in future videos how this actually comes about. And dw is equal to minus Pdv. So when you put all that together, we get that du, that's u, is equal to Tds minus Pdv. So anyway, we can see that after we've done all of this, we end up with a relation that dg is equal to vdp minus sdt. So let's compare this to dz. There's dz here. So what we notice, there is some kind of equivalence between these two things. Dz, we said, is an exact differential. We know that dg is also an exact differential. So g is now expressed as a function of pressure and temperature for this closed system, and we say that pressure and temperature are the canonical variables. So since this is the case, we can see that dg is equal to dg dp times dp. So I'm writing it in this form. Just like how we had dz dx, we have dg dp, and then we have plus dg dt times dt. So if that is the case, then we can see that dg dp is equal to v. So v is equal to dg dp. Similarly, we can see that s is equal to minus dg dt. So that's the equivalence between these different relations here. So we should also point out that when we write it in this manner, we have to be very particular and very specific about which variables that we are keeping constant. So this entire thing reduced to these two variables. So we can easily see that here we are talking about temperature being held constant, and here we are talking about pressure being held constant. So V is equal to dg dp, that is at constant temperature, and S is equal to dg dt, and that is at constant pressure. So we can now extend this relation to be valid for an open system. What happens in an open system? An open system is simply where not only is energy allowed to enter and exit, but mass is also allowed to enter and exit as well. So all we need to do is simply account for this change in mass of the system by just adjusting this exact differential of Gibbs free energy. So we have dg currently at the moment is equal to dg dp at constant temperature times dp plus dg dt at constant pressure times dt. So we just need to add in the end some kind of change in the Gibbs energy with the number of moles or the number of mass, but let's keep it to number of moles. The number of moles of different species, different chemicals, different components, or different whatever you want to call it. So since we will say that there is a multi-species system involved, so we'll differentiate it as I. So each of the different species would be I, and I would go from 1 to maybe, let's call it M, where M is the total number of species in that system. And then we would have to multiply it by D and I. So this number of moles becomes one of the canonical variables. So this quantity here, this dg dn, that is given a special name, and that is the chemical potential. We should also note here that we have dg dp, and that's at constant temperature, and now also constant number of moles, because that's one of the variables, number of moles, and now this is at constant temperature and pressure. So dg dn that is what we call the chemical potential. So we could think of these things in terms of drivers and in terms of the variable itself. So if we think about a change in the Gibbs energy associated with change in pressure, what drives that change? So the answer to that would be the rate of change of Gibbs energy with pressure. So we can just put in some of these variables here. We'll say that dg is equal to V. We saw that dg dp is V, so that's V dp, then minus S dt, and then plus this sum of the chemical potential with the number of moles. So as I was saying, a differential change in the Gibbs energy as a result of a differential change of pressure, what would drive that is volume. So a differential change in this Gibbs energy with a change in temperature, what would drive that is entropy. And a differential change in Gibbs energy as a result of change in the number of moles, what would drive that change in the number of moles is a difference in chemical potential. So this is what is actually called the fundamental property relation. Fundamental property relation. So in the course of this video, we started out by discussing line integrals, exact differential from a mathematical point of view, and we saw some characteristics of how they are defined and what they are characterized by in terms of their paths and in terms of what happens if we integrate them along a closed curve. And then we went on to extend this to thermodynamics and the different kinds of energies, and we saw that Gibbs energy is actually, an exact differential. So the mathematics of exact differentials can be applied to it. If we use the definition of the Gibbs energy, as we had seen in one of the previous videos, then we can end up with this result, which is called the fundamental property relation. So thank you very much for watching.